Right. Let's see. Let me make sure everything's good to go here. Time yet? Almost. Okay. You all have a midterm tomorrow, right? Right. So let's talk about as much of the stuff as we can. So let's begin with the following. Let's find, there's not one, the general solution of the following system of equations, system of differential equations. So we have the following. We have dx dt equal to 3x plus 2y minus 3. dy dt is equal to x plus 2y plus 1. And looking at this system, let me ask you a question. Is this system linear or nonlinear? Definitely linear. Is this system homogeneous or non-homogeneous? It's non-homogeneous. And so I suppose I have a question for you. Do you know what he expects you to do is for non-homogeneous? Does he expect you to show the substitution to another variable? Okay, cool. Right. Okay. So let's go through the process of solving this the kind of fast way that doesn't show all of the extra in between steps. So we could rewrite this as the matrix equation where we have our dx dt, dy dt as a vector, and it's equal to the coefficient matrix 3, 2, 1, 2 times the solution vector xy plus the non-homogeneous part, negative 3, 1. So there's two things we have to do. We have to solve this as usual, meaning we're going to pay attention to this matrix and kind of completely ignore this negative 3, 1 over here. We also need to find the equilibrium. And those are kind of separate pieces that we combine together at the end to write our solution. So let's go ahead, even though we're going to do this part over here, let's find the equilibrium first. I'll remind you, to find the equilibrium, you're just trying to find the one point, the one xy coordinate, where both equations are equal to 0 at the same time. So you can solve this system of equations equal to 0 in any way you'd like. Personally, since I see that both y's have the coefficient of 2 here, I'm going to subtract the second equation from the first equation because that seems like the fastest way to do it. So if I subtract this minus that, 3x minus x is 2x, 2i minus 2y is 0, and negative 3 minus 1 is negative 4. So that means x is going to have to equal 2. And then plugging that back into either equation, let's plug it back into the first one. I've got 6 plus 2y minus 3 equals 0. So 2y is going to equal, I think, negative 3. So y is going to have to equal negative 3 over 2. And I guess I give them little hats. Those are my equilibria. That is my equilibrium, singular. There is one of them into the coordinate 2 comma negative 3 halves. So what we're going to do with that is at the very end of this process, after we find our general solution, we're then going to add that on to the end. That's what we do with our equilibrium if we're not showing all the steps in between. Okay, so usual process, eigenvalues, eigenvectors, the whole shebang. In fact, I think you all should find the eigenvalues right now. So go ahead and find the eigenvalues of the matrix 3, 2, 1, 2. For those of you joining us on Zoom, we're just finding some eigenvalues of a matrix right now. We're finding the solution to a non-homogeneous system of differential equations. Let me go ahead and give you the sign-in sheet. Those are my eigenvalues. Okay, so let's switch gears for a second. If instead the question was classify the system, we would be done at this point after we wrote down that we had, or I should say classify the equilibrium, that we have an unstable node, also known as a source, right? Because both eigenvalues are positive. So always good to keep that in mind because it's probably going to come up. But let's continue on. We're going to find the eigenvectors. I personally like to do it this way, where I take my matrix 3, 2, 1, 2. I multiply it by the vector, the eigenvector that I'm looking for, and I say it's equal to, let's call it, let's do this one first, 4 times xy. So first equation, 3x plus 2y equals 4x. Subtract 3x from both sides. You get 2y equal to x. So I'm going to pick y equal to 1 and x equal to 2. So this is my lambda 2, I guess. So my v2 is going to be, I said x was 2 and y was 1. I said y was 1 and x is 2. Be careful if you say the first thing, or if the first thing you say is the second thing. Like I said, y is 1 and x is 2, and then we'll start down the vector as 1, 2. So make sure you're putting the y thing in the second spot because it's easy to say the right thing and write down the wrong thing. So then similar deal for lambda 1. I guess I could have written like lambda 2 equals 4 over here. So lambda 1, we're going to do 3, 2, 1, 2 times the vector we're looking for equal to 1 times the vector we're looking for. Again, the first equation is 3x plus 2y equal to x. Subtract 3x. You get 2y equal to negative 2x, or just y equal to negative x. So our vector v1, x could be 1 and y could be negative 1, or vice versa. I will point out, it is kind of nice to solve like y equals negative x here. And if I was going all the way here, y equal to 1/2 x, because if I was trying to say, draw the eigenlines or whatever, what I think he calls them something slightly different in class, like the vector lines or something, but like those are the equations of your eigenlines, right? Literally y equals negative x and y equals 1/2 x. So if you're trying to like draw stuff on the direction field, that is helpful. Cool, we're finding the general solution. So gotta keep going. So let's see here. So then, well, we were almost there, right? Our general solution. Now, I should point out, this is our general solution for the change of variable that we never wrote down. it would be that our other thing, which I'll make up a name for, let's call it, let's say it was instead of x and x and y, let's say it was u and v. Let's say we have uv equal to c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2, which we're going to plug in the things and say it's c1 e to the lambda 1 was, I called it 1 times t times v1 plus c2 e to the lambda 2t. Lambda 2 was 4 times t, and v2 was 2, 1. So this would be our change of variable solution. And then our actual solution, our xy, is going to be the same thing. The solution to the homogeneous equation, c1 e to the t times 1 negative 1 plus c2 e to the 4t times 2, 1 plus the other equilibrium. I forget what it was, the 2 3/2 or whatever it was. Here. 2 negative 3/2, sorry. I should also point out, if you're asked to plug in some initial conditions to find the particular solution, you have to wait until after you change back. But you can't from this change of variables here find the C1 and C2. You have to wait until after. So if we pretend that, or we don't have to pretend, let's say we were given an initial condition of x of 0 equal to 5 and y of 0 equal to 3. Sure, that seems probably not terrible. Let's go ahead and solve for C1 and C2. So find C1 and C2. I'll let you all work on it. So those are the equations I'm getting after plugging in 0 for t and 5 and 3. Oh, 5 and what? 5 and 3, not 5 and 0. Geez. So plugging in 5 for x and 3 for y and 0 for t, we get these equations. 5, 3 is equal to c1 times 1 negative 1 plus c2 times 2, 1 plus this. Then we subtract that over to this side. So this should be 3 plus 3/2, which is not 3/2. That is 9/2. But again, you're just solving a system of two equations and two variables, whatever process you like. Here I see that the C1s will cancel if I add these together. So adding these together is going to give me 3 plus 9/2, which is 6/2 plus 9/2, which is 15/2, equal to 0 C1 and 3 C2. So dividing by 3, it looks like C2 is going to equal 5 over 2. And then if I can solve for C1, 9 over 2 minus 5 over 2 is equal to negative C1. So 4/2 or 2 is negative C1, so C1 is negative 2. And then technically you should probably go back and write the whole solution with the C1 and C2 plugged in, but like, let's not. Right. So I feel like let's make sure I did this right, because I feel like the faces are looking at like I made a mistake.
We don't need to add the two and then hit.
I did. I didn't show that work. So I subtracted 2 from 5 to get 3. And I added 3 halves to 3 to get 9 halves. Yeah. So then, right, we could write our actual solution is -2 e to the t times 1 -1 plus 5 halves e to the 4t times 2 1 plus 2 -3 halves. Cool. So non-homogeneous, not too terrible. Interesting. What else could we be asked to do with this? Sure. Let's do one more. Yeah, yeah. I'm just trying to think about. Yeah, let's draw the. Let's also. Oops, that's. While we're at it, let's go ahead and graph x as a function of time and y as a function of time for our particular solution. Now, the nice thing here is that you've already actually got the equation. So it's not even so much of an estimate, it's just kind of knowing what we're looking at. So if we look back at our general solution here for a second, let's see what we've got. We've got x of t, the top row of this solution is our C1, which I already forgot what it was. I think it was -2. Yep. So it's -2 e to the t times 1 plus C2 was 5 halves, I think. Yes. 5 halves times e to the 4t times 2. So I'm going to say 5 times e to the 4t plus 2. And then y of t would be the bottom row. Y of t is going to equal -2 times -1, so +2 e to the t. And 5 halves times 1 is 5 halves e to the 4t minus 3 over 2. So the question though is how would you actually graph this? And again, we're not trying to do a great job here. We're trying to do a good enough job. So looking at x of t here, I'm really going to focus on two things. I'm going to focus on what my initial value is. Well, you already know what it should be. They already told us that information in the problem. X of 0 was 5. Cool. There's 5. And then the question is, does it get bigger or smaller? Well, maybe a little bit of both. You've got this negative part here, this positive part here, but you can see that the e to the 4t is going to get bigger faster than the e to the t. So this positive part here is going to overpower this negative part here. It might dip down first a little bit. I don't actually know, to be really honest. Like, I don't know what this graph looks like actually. If I was graphing it, I might try to do, no, I really don't think so. No, I kind of just think I would maybe dip down a little bit and then say it's going to look vaguely exponential and something like that. If you want, we can check our work and see how it actually looks. Because now I'm curious. We take a look here. We've got, sure, I'll graph like this. Y equal to -2 e to the x plus 5 e to the 4x plus 2. So clearly I didn't get it exactly right. It's not dipping down at all a little bit. It's just going straight up. I'll live. It's not that big a deal. As long as you've got a decent idea of what eventually it looks like, it's probably not a huge miss if you miscalculate where if it's dropping down first or not. But 1 second. But really, this question is not a great question here because really you're getting asked this question if you have like the direction field to kind of think about what X is doing before you're actually trying to graph it. Question. Let's double check. So the y of t part was going to be so it was, but so carefully, it's the -2 times e to the t times -1. That's why it's +2 there. Yeah, so here's your t and your x of t, although not really. And then for t and y of t, that's a little bit easier. So again, if we plug in 0 for t, we're going to get exactly what our initial condition should be, which is 3. And then here we're just going up and up and up, right? As t gets bigger, each of these things gets larger. So we're just doing something like that. But all these graphs eventually, well, no, yeah, I should say, all these graphs that you might get asked to graph, like unless it's a spiral, but if your system is a node, whether it's stable or unstable, or a saddle, you're going to have exponential growth or exponential decay eventually. I could see, yeah, well, I'll come back. I have an idea, which we'll come back around to later. So yeah, that's all I have for that. Let's look at something else here. Where'd you go? Not you, not you, not you. Where'd you go? All right, 1 second. There we go. So, question 2. That's, um, for the following system, find all equilibria and determine their behavior, their local behavior. So let me ask you, before I even write down the equations, the wording of this question makes you think I have what kind of system? Homogeneous, non-homogeneous, linear, non-linear? It's giving non-linear, right? Very much so. Like this is the phrasing here is for sure pointing you at a non-linear because one, you're finding more than one equilibria, which is a hallmark of a non-linear system, although a non-linear system could have a single equilibria. But more importantly, determine their local behavior is really a key. Oh, yeah, that's for sure going to be non-linear because locally things are happening, but globally it's all over the place. So here's our system of equations. Dx dt is equal to xy plus y squared minus 5y, and dy dt is equal to 6x minus 3xy. And so, of course, to find the equilibria, we're going to set each of these equal to 0, and then we're going to try and deal with the one that's easier to deal with first. So, in my opinion, the second one is easier to deal with first, because from the second one here, I can factor out a 3x and say, excuse me, 3x times 2 minus y is equal to 0. So I'm either getting x equal to 0 as half of an equilibrium or y equal to 2 as half of a different equilibrium. So then I'm going to look at my other differential equation and plug in either 0 for x or 2 for y to see what the corresponding coordinates are going to be. So for the other equation, if I plug in x equal to 0, I'm going to get 0, which I'm not going to write down, plus y squared minus 5y equals 0. Factoring out a y, I end up getting either y equal to 0 or y equal to 5. So my two equilibria from this part are going to be x is 0, y is 0, and x is 0, y is 5. But then I still get to look at what if y was equal to 2? So if y is equal to 2, then we're going to have 2 times x plus 2 squared minus 5 times 2 equals 0. And solving for x, we're going to get, let's see, 2x minus 6 equals 0. So x is going to have to equal 3. So my other equilibrium here is 3 comma 2. And those 3 points are the only 3 points that make both equations equal to 0 at the same time. Cool. Now we're going to classify them. And to classify them, we have to find the Jacobian of the system. So our Jacobian matrix, and again, this is where I definitely would encourage all of you to write down, even if you don't need it for yourself, write it down for the person who's grading your work. Write down that the first differential equation is F, the second differential equation is G, and that your Jacobian matrix that you're going to find is partial of F with respect to X, partial of F with respect to Y, partial of G with respect to X, partial of G with respect to Y. Unless you're already given that on your life formula. If it's given on the formula sheet, okay, don't write it down. Don't waste your time. But if it's not, you're showing someone you know a thing, which is good to show people. So then we're going to find the partial derivatives. It's also good to write this down because at least if you make a mistake in the next part, they knew that you knew what you were supposed to do, even if you made an error doing it. So let's see, our fx here is going to be 1 times y plus 0 plus 0. Our fy is going to be x times 1 plus 2y minus 5. Our gx is going to be 6 minus 3y. And our gy is going to be 0 minus 3x. Cool. Some typical good news in these situations is a lot of the times after you plug in your equilibrium to the Jacobian, it's very, very easy to identify the eigenvalues. Not always, but often. So let's check and see what we've got. So let's look at 0, 0 first. So j of 0, 0 is going to be 0. 0 plus 0 minus 5 is minus 5. 6 minus 0 is 6, and 0. So this one actually is not obvious. I was hoping for something that had a 0 in one of the places there isn't a 0, but we got zeros everywhere, everywhere we didn't want them. So we actually have to find the eigenvalues here. So we're going to say that determinant of negative lambda, negative 5, 6, negative lambda equals 0. So we're going to get lambda squared minus negative 5 times 6 equals 0. So lambda squared plus 30 equals 0. So what are my eigenvalues going to be? It looks like they're going to be plus or minus the square root of negative 30. So what my eigenvalues are imaginary. It's a spiral. What kind of spiral? Stable? Unstable? Neither. This is a neutral spiral because there's no real part, right? This is equal to 0 plus or minus I root 30. So this is a neutral spiral. How annoying. Also called a center. Okay, let's look at the other ones. We have J of 0, comma 5. Let's go ahead and remind. So let's have our Jacobian still in view though, so we know how to calculate things here. Okay, so plugging 0 for x and 5 for y, we're going to get 5, and then 0 plus 10 minus 5 is also 5. And then 6 minus 15 is negative 9, and then negative 0. So I know I said a thing before about how they're often easy, but clearly the example I made up is not. Question. I wouldn't say it's a circle. It's more of an oval. But its path is that it keeps just going on itself, right? It doesn't go inward or outward. But yeah, a circle is not quite right because it might be wider than it is tall or taller than it is wide, but it is a circular path. Or elliptical is probably the right word. So let's see here. I would also point out you could use the trace determinant criteria if you're comfortable using that. Um, but it's really usually not easier in my opinion. So we're going to have determinant of 5 minus lambda, 5, negative 9, 0 minus lambda. And we're going to get 5 minus lambda times negative lambda. Minus 5 times negative 9 is minus negative 45. So I've got lambda squared minus 5 lambda plus 45 equal to 0. This probably isn't going to factor. I don't know numbers that multiply to 45 and add to negative 5. I don't think anyway. Nope, I don't think so. Close, but no cigar. So our eigenvalues are going to be negative negative 5 plus or minus the square root of negative 5 squared, 25 again minus 4 times 1 times 45, all divided by 2. Okay, this is where you should stop. You should ask yourself, are my eigenvalues real or imaginary? They're definitely imaginary, right? The square root has a negative number inside it for sure. And the real part is positive this time, So we have an unstable spiral. Unstable, I can spell, sure. We also knew it was going to be unstable if it was going to be one of these things that was unstable because our trace was +5. All right, let's hope I know I mean let's hope, but I doubt the next one's going to be any better than the previous two. So let's see. So our last one, J of 3, comma 2, plugging into our Jacobian. So y is 2, so it's going to be 2, and then we have x plus 2 times y minus 5. We have 6 minus 3 times y. Oh, this one works out nicely. 6 minus 3 times 2. And finally, negative 3 times 3. So this matrix is the one I was hoping for, I guess. So we get 2, and then 7 minus 5 is 2, and 0 and negative 9. And this one, you all should be able to tell me immediately what the eigenvalues are. They are +2 and negative 9, which means we have a saddle. So lambda equals 2 and negative 9, saddle. Let's see, there's another one I want to make sure we got too. Is there anything else we can say about this? I don't think so. Yeah. All right, let's look at another problem, which is not super different in general, but requires more reading comprehension. So I want you all to try to do this problem. And I can zoom in if that's hard to read. Okay, that should be hopefully readable. And so the first part is just asking you to try to write down the system of differential equations being described here. I'll take a look and see what we can come up with there. Make sure I've got the right problem over here. Let's over here for a minute. So, to me, this screams we need to draw a diagram. bacteria are in two different patches, A and B. The bacteria in patch A are increasing in number at a rate of 4 per capita and moving to patch B at a rate of 2 per capita. So now I'm like, now I'm trying to think about like how do, so XA and XB are the number of bacteria in each in patch A and patch B. So we have XA here, XB here. Construct a system that describes what we have above. So we're increasing number at a rate of 4 per capita. So I'm trying to think about the right way to draw that in a oh my gosh, in a compartment diagram. I'm trying to think if this is really a compartment diagram. Now that I'm actually asking myself, like, usually we don't have stuff going back in on itself. But I want to draw something like this, where it's like doing like that. Let's scratch that for a second. So here's what I do know. Bacteria in patch A are increasing in number at a rate of 4 per capita and moving to patch B at a rate of 2 per capita. So basically we have two guys moving from there to there. And that'd be two, I guess, XA, right? Every member of XA, two for everyone is moving over, right? That's what we're saying, 2 per capita. I know you guys can't see the words anymore. Sorry. I'm looking at the words and you're not able to see the words. So I'll remind you what we're saying here is that the bacteria in patch A are increasing in number at a rate of 4 per capita. So I guess I'm going to draw this even though I don't love it. And patch B, sorry, and they're moving to patch B at a rate of 2 per capita. Similarly, the bacteria in patch B are growing in number at a rate of 4 per capita as well, and moving to patch A at a rate of 3 per capita. That seems to me to be the right compartment diagram for the system. I think. Let's see what the system of equations looks like. So let's see. Our dxa dt would be, well, let's see. What's coming into xa? We have 4 times xa, we have 3 times xb. What's leaving out of xa? 2 times xa. We'll simplify this in a moment. Similarly, what's happening with xb? Well, we have 4xb going into xb and 2xa going into xb. So 4xb plus 2xa, and we're losing 3xb. So this looks like we should have dxa dt equal to 4xa minus 2xa is 2xa plus 3xb. And dxb dt is equal to 2xa. And then 4xb minus 3xb is plus 1xb. Interesting. Which I would say is a system we should work on, except I think that's exactly the matrix we already kind of worked with. Well, technically not the exact same. The matrix we started with, and the other problem was 3, 2, 1, 2 instead of 2, 3, 2, 1. But if we were to say classify the equilibrium 0, 0, well, again, this should be the question you're happiest to see. In my opinion, like classify the equilibrium is like, cool, I know what to do. Find the eigenvalues and then say the right thing based on the eigenvalues. So do it. All right, let's see what we've got here. So determinant of 2 minus lambda, 3, 2, 1 minus lambda. We're going to get 2 minus lambda times 1 minus lambda minus 6, which is lambda squared, minus 3 lambda, plus 2 minus 6 is minus 4. So we're getting lambda minus 4 times lambda plus 1. So we have eigenvalues of opposite signs, meaning we have a saddle. So I was looking over what he kind of posted about like what is potential fair for your exam. And to me, it feels like it's a lot of just like this kind of stuff, like solving systems, classifying systems. That's kind of the everything. And I know it might feel like a lot of things, but it's really kind of just one giant concept that you're applying in a few different ways. So honestly, the best thing to do is probably just to do some more practice. So let's do another one. But I'm gonna make you guys do all of it this time. So let's see. I've got let's not make it too terrible. Sorry, where'd you go? I had my example ready to go and I lost it. Pardon me, 1 second. Sorry, I've got a bunch of examples up and I keep losing track of where they are. Where'd you go? Nice example I had all ready to go. Pardon me while I look for the thing I just had in front of my face. Sure. So I want you guys so here's the setup. Your system is given by this matrix equation, dx dt, dy dt equal to 2, 1, negative 1, 2 times xy. So, um, so let me double check one thing here. I think, sorry, now I have to actually double check something because I think this example is not what I think I'm missing a sign somewhere. Apologies. Let me change some signs. Negative 2, positive 1, positive 1, negative 2. Now let me double check that. Sorry, I'm trying to make sure it's not one where you have terrible negative, or sorry, a negative discriminant. And your trace here is negative 4. And your determinant would be 4 minus 1 is 3. That should be fine. Okay, cool. So yes, all right. So find the general solution. And then after you find, whoops, and then after you find the general solution, I'll give you some initial conditions. I'm gonna give you like 5 minutes, I think should be probably enough time. It depends. All right, that's 5 minutes, and I can't be quiet any longer than that. So, um, eigenvalues, I believe, should be -1, -3. Seem Does seem like what people got. Good. Okay. So also we know stuff already, right? We know it's going to be a stable node. Eigenvectors. Let me go ahead and find them the other way. I don't usually like to do it, just so you can, if you like doing it that way, you can be reminded of how that works. So instead of doing my matrix times my eigenvector equal to lambda times my eigenvector, I'm going to do A minus lambda I times the eigenvector I'm looking for equal to the zero vector. So that way it's -2 minus, let's do lambda equal to -1 first. -2 minus -1, 1, 1, -2 minus -1 times the vector you're looking for equal to the zero vector. And so both equations are, well, -1 times. So the thing you should notice about these equations is that right from the get-go, both equations should look like multiples of each other. Right? The first equation is -x plus y equals 0. The second equation is +x minus y equals 0. So really, both equations are really genuinely very much the same from the get-go. In this case, we get y equal to x. So our eigenvector is going to be 1, 1. Similarly, for lambda 2 equal to -3, we're going to have -2 minus -3, so -2 plus 3, 1, 1, and then -2 plus 3. So now it's just, both equations are 1x plus 1y. So we get x plus y equals 0. We get y equal to -x. So our second eigenvector is x is 1, y is -1. Or x is -1 and y is +1. Either way, totally fine. So our general solution is x of t, y of t equal to c1 e to the -1 times t times v1 plus c2 e to the -3 times t times v2. I want to remind you all, even though it's not 100% important to know, that I think it's pretty important to know this, that the reason that these negative eigenvalues correspond to our equilibrium being stable is because as time goes on and on and on, e to the -t is going to get smaller and smaller and smaller. E to the -3t is also going to get smaller and smaller and smaller. So essentially you're getting c1 times 0 times 1, 1 plus c2 times 0 times 1, -1, which just gets closer and closer and closer to 0, 0. That's why these negative eigenvalues give us a stable equilibrium of 0, 0. And then to find our particular solution, we're going to plug in our initial conditions, which was x of 0 equal to 2 and y of 0 equal to 2. So we're going to say that 2, 2 is equal to c1 times e to the 0, which is going to be 1 times 1, 1, plus c2 times e to the 0, which is going to be 1 times 1, -1. All right, so we have 2 equal to c1 plus c2 and 2 equal to c1 minus c2. Oh, that's interesting. This is an interesting solution here. So adding these together, we get 4 equal to 2c1 plus 0. So c1 is equal to 2, which means c2 is equal to 0. So interesting. So that means our particular solution here is x of t, y of t equal to 2 e to the -t times 1, 1. End of story, because our C2 is 0. Let's talk about what that means graphically. So let's say after this, we were asked to draw the phase plane with the, what does he call them? There's a word he uses that I'm trying to use as well. Um, Draw the phase plane with that's the other thing I'm looking for, the eigenvector directions. I just call them the eigenlines, but he says eigenvector directions. So we're going to draw the eigenvector directions and the nullifying directions. Okay, so the eigenvector direction should be super duper easy to draw. So phase plane here. I'm trying to use some different colors. So first, let's do the eigenvector directions. So my eigenvectors were 1, 1, and 1, negative 1. They're super easy to draw. For the eigenvector 1, 1, simply go over to the point 1, 1, and then draw the line that goes through that point and the origin. Or try to draw the line that goes to that point. I said it's super easy to do, but you have to be able to draw lines. And that was for the eigenvalue, which was negative 1. And then for the other eigenline, which was the eigenvector 1, negative 1, go over 1 and down 1. So, and then draw that line. These two happen to be very nice in that they are perpendicular to each other. That is not always the case, but this example is kind of cherry picked in that way. And that was for lambda 2 equal to negative 3. And for the eigenvalues that are negative, the arrows on the eigenvector direction lines should point inward, straight towards the origin. If the eigenvalues were positive, the arrows would point outwards. And now let's draw the null lines. So let's look back at our original equations, which I've forgotten. Our original equations were dx dt equal to negative 2x plus 1y, and dy dt equal to positive x minus 2y. So our x null line, we're going to get by setting that equal to 0. So we're going to get negative 2x plus y equal to 0, or y equal to 2x. Let's draw that one in red. So along the line y equal to 2x, that is our x null line, where dx dt is equal to 0. So on that null line, all of your little direction arrows better be purely vertical. And since we've already drawn these eigenvectors, I'm pretty sure that the ones up here are going to be pointing downwards. And the ones down here are going to be pointing upwards. Again, we also know it's a stable node, so we know things should be kind of pointing towards the origin. Similarly, in green, where's my good green pen? I have a green pen that's not very good. Where's my other one that's really good? Sorry. Nope, I've lost it apparently. Not you, not you, not you, not you. Did I really lose it? I'm losing my mind. That's what I'm losing. Fine, we lose purple. Okay, so for my other one, for my y null line, we have negative x minus 2y equal to 0, or solving for y because it makes it easier for me to graph it, I'm going to have y equal to 1/2 x. I see a question. Yeah. Yeah. But really what I'm actually doing without doing it is I'm saying, I know that since my eigenvector lines are pointing that way, any point in between them has to be kind of pointing in the same direction. Or if you like, you can test a point, right? If I actually plug in x equal to 1 and y equal to 2, well, dx dt had better be 0, because if x is 1 and y is 2, you get 0. But in the other equation, if x is 1 and y is 2, you get 1 minus 4, which is negative 3. So your dy dt at the point 1, 2 is negative 3 pointing downwards. So that's another way you can get there if you don't just see it from what you've already drawn. Sure. Right. Right. It's just that sometimes that becomes cumbersome. It's time intensive, right? You're using a lot of time to test multiple points, where with practice you can kind of see, oh yeah, we can see what's happening here. So my other null line is y equals 1/2 x. Don't draw the arrows at the end, James. And then here, all my things should be pointing purely horizontally because this is dy dt equal to 0. So everything is going like that. And these ones should be pointing left. These ones over here are pointing right. So let's talk about drawing a, oh, question.
Do 1 point, because that's how, he said we have to do that on the test.
Did you have to like plot a point?
Instead, like, of just like assuming that it's going in that direction.
So does he want you to like plot a point on the actual line?
Yeah.
But does he want you to test points or on your lines and null lines or between? Right. Okay. Cool. Yes, we can definitely do that. Sure. So let's test a point over here on the x-axis. So let's test the point, say 2, 0. So at that point there, I can see that dx dt is going to be -4 plus 0, and dy dt is going to be 2 minus 0. So I'm getting, at that point, a direction vector of -4 comma +2 at 2, 0, meaning we're going left and up. Left and up? That seems interesting, James. But it is what we're getting, right? If x is 2 and y is 0, we're going left and up. But more left than up, so we're kind of going that way. Oh, that makes sense. Why do I think that makes sense? Good question. Well, here's what I can see is going to happen. From there, if we were to draw the trajectory from there, we can't just go straight like into the origin because you have to follow the path, right? And the thing here is that right there, we still have some, we're kind of between these two things here where this is pushing us up and left and this is pushing us purely left. So we're definitely in a section where we're going up and left. And then we're going to cross this null line, and we can only cross a null line purely, in this case, horizontally, and then come back down like that. Yeah, I don't love drawing all the little arrows. But then, so here's what I always remember is true. Whenever you go to the other side of a null line, basically, how do I say this the right way? On the other side, you still have to be pointing left, but instead of pointing upward, you're going to be pointing left and downward. So like up here, you're pointing left and down instead of left and up. And over here, you're going to be pointing right and down. And so on and so on and so on. What I wanted to mention was our particularly interesting initial condition of 2, 2. So we started at 2, 2, and oh, look, we started exactly on one of the eigenvector direction lines, meaning our situation was purely that eigenvector, and the other one got completely left off, which is why our particular solution looked exactly like that, where we had one eigenvector with its coefficient and the other coefficient was 0. And so if you draw the trajectory from that initial condition, it's not very exciting. The trajectory, we've already drawn it, it looks like this, straight in towards the origin. If you happen to start on an eigenvector line, you're either moving straight in towards the origin if your eigenvalue is negative, straight away from the origin if your eigenvalue is positive, along that eigenvector line direction. And then you could try to draw other trajectories. You might have noticed it's not the part I'm very good at, so I try not to do it very much. But I'll point out, like, for example, if you were to say we started at the initial condition of 1, 4. We want to draw the trajectory there. Well, we know we're going down and to the right. And then when we cross this red null line, we better be purely vertical. So we're going to come at it like this. We're going to cross it so that we're moving vertically. And then we change directions. We're still going down, but instead of going down and right, now we're going down and left. Like that. So that's what I mean that when you cross a null line, you change directions, right? This part has to be purely vertical. On one side of it, you're left and vertical. On the other side of it, you're right and vertical. Or over here, this purple null line, which is a little bit hard to see, On one side of it, you are left and up. On the other side of it, you are left and down. Which I didn't draw very well, but I'm trying to see it. Let's look at one more thing here. Where'd you go? Not you. Okay. So here's a question that looks relatively challenging. But so I can see it, so I can see it better. Let me copy this and also paste it over here on my screen that I can see better on. Maybe it'll come up. Maybe it won't. No, I know why it's not. Okay, fine. Fine. Sorry, sometimes I do stupid things. There we go. Okay. So we're being asked to match the system with the phased portrait and to briefly explain why it is what it is. Ugh. Does this seem so? First, I should ask you, does this seem like a question your instructor would ask? No, not really. On the homework, maybe, but not on an exam. It's probably not worth our time, I guess. Seems like a fun problem, though. So, what I would point out is if you were asked something like this, you definitely want to look for the equilibria. So, like, I can see one of the equilibria is obviously 0, 0. And it looks like all these have it. This one has 0, 0 in the equilibrium. Clearly, like weird shit's going on here. 0, 0 there. And so all these have 0, 0. So you probably have to start looking for other equilibria as well. Or maybe try to look at the Jacobian to classify what 0, 0 looks like to kind of guess, oh, is 0, 0 looking like an unstable node? Or is it looking more like a saddle? Or I say that all three of these look pretty unstable node-like for the origin, whereas this one looks more like a saddle. So it's probably not that one, because it's probably going to be one that's harder to figure out. But again, if that's not something you might encounter, then it's probably not the best use of our time. So I guess I should say, well, there's my arm. Okay. In the last, 15 minutes we have here, I don't have a whole lot else to say. So I should ask you all, do you have any specific questions you would like me to address? If I can, I feel like we've kind of covered most of it. I was going to give you a linearization to work on, but it's not in any of what you wrote as far as what's on your exam. So I didn't think that was a good use of our time. Sure. Let's see here. Sorry. Sorry. Papers. No. Let's see if I can write one that has a more kind of interesting situation going on here. So let's say, let me instead of giving you a system of equations, let's just give ourselves the features that we need to draw. So here's what I want you to draw: the phase plane with the following. Your x null line is the line y equal to x. Your y null line is y equal to negative 2x. One of your eigenvalues is positive 2, and the eigenvector associated with that is the eigenvector 1, 2. And your other eigenvalue is negative 3, and the associated eigenvector is, sure, negative 3, 1. Draw the phase plane, and then plot the trajectory for the initial condition, x of 0 equal to, let me be careful here. Sure, x of 0 equal to 1, y of 0 equal to 3. Seems like it might work out. Oh, I should pass on the attention. Yeah. For what? Hmm? Mm-hmm. Okay. Okay. We can do that. Sure, sure. Right. So the problem with this question is that you don't have the information to do that, right? Because there's no, I didn't give you the system of equations to plug in. This, right?
So for this way,
Mm-hmm.
like you can be to the because I think you can go like you just the no content that is what's supposed to be. Because we haven't printed that.
Yeah. Hmm.
Because I think I would usually see.
That. Let's take a look at what we've got here, because maybe this question, I feel like this question is written or designed kind of okay, but maybe not exactly how it's going to come up for you in your exam. So let's see what we've got. I feel like the problem with having the equations is then like, as opposed to just drawing the whole thing, why not just solve the system? And so I feel like that's kind of why I was trying to avoid coming up with equations that we could actually just solve. So let's look at our null clients here. So our x null client is y equal to x. So that's your usual line that's going that way. And we don't know really which way the arrows are going at all because we don't have the equations, but we know that they should be purely vertical. This is dx dt equal to 0. We know things are going up and down on that. Same over here. And they should change directions when you cross the equilibrium. So these can be up and these can be down, or these can be down and these can be up. And then for our y null line, which is y equal to negative 2x, it's going to look like this. And again, all those arrows should be purely horizontal. And then we have our null climbs, sorry, our eigenvectors. So the eigenvector 1, 2, it's going over 1 and up 2. So it's going to look, let's use a different color here. Let's use red. So over 1, up 2, it's going to be looking like that. And that's for lambda 1 equal to positive 2. So we know that along that eigenline or that eigenvector direction, we should be pointing away from the origin. Which you could also, so I'll point out, if you took a point like somewhere in here and plugged it into your differential equations that we don't have, you should be getting here that, oh, the dx dt is negative and dy dt is also negative because we're going left and down. Or over here, dx dt would be positive and dy dt would also be positive because we're going up and right. And then similarly, for my eigenvalue of negative 3, our v2 is negative 3, 1. So we're going left 3 and up 1. So our eigenline looks like this. So yeah, I guess back to your kind of statement, the eigenline kind of does the work of plugging in a point between your two null clients to kind of see which way you're going. As long as your null client isn't the same as your eigenline, which it can be sometimes, which is less than ideal in my opinion. That's usually only when you have like an upper or lower triangular matrix. Like when you have like, the nice easy cases where you can find the eigenvalues really easily, those usually come out where one of your eigenlines is also a null line because it's usually one of the axes. So here, this one for lambda 2 equal to negative 3, these are all going to be pointing inward towards the origin. So like something over here between these two had better be pointing left and up. Or over here, right and down. And then if we look at our initial condition of 1, 3 up here. So I should point out, at this point, we also know which way the null clines are actually pointing, right? This dy dt equal to 0, these should all be pointing right because they're between two things that both point rightward. And these ones should be pointing left for the same reason, or for the same type of reason. And these ones should all point up. And these ones should all point down. So now if we start at this point right here, well, we're between these things pointing us right and up. So we're going to go right and up and we're going to get asymptotically closer to that eigenline. Which is maybe not the most exciting answer. I was hoping to, so I kind of wanted one, like, so let's say we had started at a different point. Let's say we started at negative 5, 1 right there. This one's going to point us which way to start. Left or right? Up or down? Down. So we're going to write down, but then we're going to, right, since we're kind of close to this one that's pushing inwards, we're going to kind of move inward, but then eventually we're going to have to cross this null cline and then move down and left, getting closer to the asymptote with the, to the eigenline with the positive eigenvalue. So when you have a situation like this where it's a saddle, because one of your eigenvalues is positive, one of your eigenvalues is negative, unless you start off on the eigenline with the negative eigenvalue, you're always going to end up getting closer and closer to the eigenline with the positive eigenvalue. Oh, there was something in a problem the other day that someone asked me about, like, oh, there was some weird phrasing, like, I don't remember. There was some like weird, like the, no, I don't remember what it was, but it was basically like, it was talking about when you start off on the eigenline with, it's like oh my God, the manifold. It was the manifold. There was someone asked me a question about the manifold that someone used. And I feel like it was in your class because like, this is the only class that's talking about this kind of stuff, but maybe it wasn't. But they were talking about how like, this is like the one direction where you get a solution going towards the equilibrium and everything else moves you away from it. So it's But yeah, I don't remember where it popped up. Just I remember it showing up. Shouldn't worry about it anyway. It's not a big deal. But I was trying to address the question I had heard earlier. So really here, kind of the thing I would say that's important to remember, like if you are trying to draw the initial condition, or I should say the trajectory for starting at some point like here, like 4, 1, you have to cross the null climb in the appropriate purely vertical or purely horizontal direction. Right? So up here, right, you have to cross this purely vertically. Or starting over here, you have to cross this guy purely horizontally. And I imagine if you have to draw trajectories like that, that is something that they will be looking for. So we've got a minute left. Let's say let's draw x of t and y of t for the initial condition 4, 1. And this should be comparatively easier than the previous thing. So my point here is that if you look at this trajectory starting at the point 4, 1, do the x values start off getting bigger or smaller? Well, which direction are we going? Left or right? From this starting point here. We're definitely moving leftward, which means the x values are getting smaller. So if we're drawing x versus t, we're starting off at an x value of 4. We're getting a little bit smaller, maybe down to like an x value of, I don't know, 3. And then we're getting bigger and bigger and bigger forever and ever and ever. On the other hand, the y values, we started at a y value of 1, and the y values don't get smaller. They just keep getting bigger and bigger the whole time. So the y values, just like that. I could see asking someone to draw a trajectory like this and then asking to draw x and y and being very kind of focused on the fact that you better draw x decreasing first a little bit because we're moving left before we start moving right. All right, that's all I got. Good luck on your test tomorrow. You'll all do fine. Just remember the things. Ah, it sounds like you like just remember what you're supposed to remember. You'll do fine. But really, I think you guys will do fine. You've seen this a lot. I think you are prepared and ready to go. And I have office hours over and drop in if you want to ask more questions.